Hello everyone, welcome back to the course. Today we'll learn a very important topic, which is the behavior of oil in the environment. So it's more related with the spill management, and your project work would be highly dependent on this topic. So I would suggest you to focus about this topic much. Now, before even starting the rest of the presentation, we'll watch a video. That video link is already in here, so we'll actually watch the video to know what is the oil spill and how the oil spill actually um, can be modeled and how we can actually predict the oil spill. Because before we have learned at the previous lecture what are the properties of oil. Now let's see how the oil actually will behave if it's spilled in the water. Okay.
During the threat of an oil spill, NOAA predicts where the oil might spread. To predict where oil might go, we model how weather, wind, tides, and currents affect oil movement. But natural variability in wind, weather, and water currents can change the trajectory of a spill in ways difficult to predict. To get the best forecast possible, we use aircraft and field observations to monitor the actual course and extent of an oil spill. These observations are then fed back into our computer model to improve the next forecast. Predicting the trajectory of an oil spill is tricky, but having better data and technology helps us show where oil is and where it could spread. Knowing where the oil is and where it is going is a key component of oil spill response.
All right. So as it says in here, like knowing where it's going, and it's also important to know the environmental factors and everything. So we'll actually learn everything about the oil spill this presentation. So the oil spreads rapidly on the water after it spills. Okay, so if the slick is near to the land and the wind is less, then the speed of the oil slick would be like the speed of spreading would be like 10 kilometer per hour. Okay, on the and and if the wind is more than 20 kilometer per hour in an open sea, then the oil is moved predominantly by the wind. Okay, so that means if just see the comparison. If it's the wind speed is less than 10 kilometer per hour, then only 3% of the whole speed would be dependent on the wind. Okay, rest with the wave. Okay, or like the ocean current. But if the wind speed is higher, like 20 kilometer per hour, then it's mostly driven by the wind. Okay, that's how it actually correlated. um, the reformation of droplets and the tar balls and tar mats have been observed also, and the binding force is simply due to the adhesion. Okay, now let's see the effect of the wind and current. Now, um, if this is the current component, like the ocean's wave, okay, the force, okay, and if this one is the wind component, okay, here. So if the wind is in this direction and the ocean's wave movement is in, sorry, is in this direction, okay, in that case the resultant is over this direction. So this is the sea wave and this is the wind, so the resultant of the spill would be in this direction. However, um, if the current is in this position and wind is in this direction, okay, so the resultant would be in here. So as you can see, it didn't vary much. Why? Because if the wind is less than 10 kilometer per hour, in that case the velocity will be much higher. But if the wind is for instance like 20 kilometer per hour, okay, then what gonna happen, then you will find like the wind direction will actually have a very important significant effect on the movement of the oil slick. So oil slick means oil spillage. Okay, so this is very important to know actually when we actually model the spillage. Now the movement of oil and spill modeling. So after the oil has been spilled, the oil tend to spread into slick. Slick is the, as I said, it's the thin film. Okay, so for instance, this is the water, and the oil spillage happens. So on the top of the water, there will be oil spill. So this film is known as the slick. Okay, now over the surface of water, this slick has been created. Now, for the lighter component, okay, if it's a lighter component, for instance the light crude oil or gasoline or the diesel, okay, what's going to happen in this case, the slick would be thin. Okay, but for heavy crude oil, so bunker c is a very heavy oil. Okay, the slick is not that much thin, it would be several millimeter thickness. Okay, so we'll see that later on. Now oil spread evenly over the water surface. Okay, even the absence of the wind and the waves. Why? Due to the gravity. All right, so if this is the water, okay, and if you actually put some oil in here, then you'll find like the oil actually spread around slowly. Okay, why it is that? Because due to the gravity and also the interfacial tension between the oil and the water. Okay, so if the viscosity of the oil is less, then the spreading would be higher. If the viscosity is more, then it would be lower. Okay, so viscosity of oil oppose this force. All right, so over the time, for first few hours, the importance of the effect of gravity diminish. All right, over the few hours. So for first couple of hours, the effect of gravity is higher, but after that the effect of gravity diminish. Why is that? Because how gravity actually works. So for instance, this is a big drop of oil, it actually spill to the water. For instance, this drop weighs like 100 gram of oil I have. Okay, or for instance 100 ml oil I have. Okay, now if we actually put this chunk in the water, then this weight in here in this surface area. Okay, but when it actually drop in the water and it's spread around, okay, so after that the whole thickness of the oil will be a couple of like several millimeter, and it's already spread around. So the gravity works in this lump, and gravity works in this bigger area with a thin film or thin slick will be different. Okay, so that's why uh, after a couple of hours, when the oil has been sufficiently spread around, after that the gravity diminish. Okay, however the interfacial tension continues to spread the oil. So that means the first couple of hours gravity was the predominant. Okay, but after that it's mostly the interfacial tension become more predominant. Okay, so let's look at that. What is this? This is a figure. It shows different oil, gasoline, diesel fuel oil, and goes to the bunker and emulsion. That means viscosity. Sorry, it will be other way around. Yeah, so this is low, high. Okay, so here is the lower viscosity and here is the higher viscosity, and this is time. This is 1 minute, one day, and 96 hours. Okay, so what we see in here, you can see for the gasoline. Okay, right after spillage, after 1 minute, it's spread around in this area. After 24 hours, it's gone, and definitely 96 hours you won't find a single droplets or presence in that. Okay, now in case of diesel fuel, like it spread the same area as the gasoline. Okay, like this area, very similar. 24 hours, gone. Okay, you'll find a little bit actually, but after 96 hours it will be totally gone. Light crude oil, you see the spreading area is only this much after 1 minute, but after 24 hours it expands, right? And after 96 hours, not much. Okay, so if you see the bunker fuel, this is after 1 minute, this is after 24 hours, and this is after 96 hours. So this is a very, very important illustration. Why is that? Because in case of gasoline, what's happened? It is more volatile. Okay, so and also it can spread more, much more better. Why? Because lower of the viscosity. So since the viscosity is low, so it spread rapidly, and since it's more volatile, so it's totally gone. Now light crude oil is less volatile, I mean moderately volatile. Why? Because the viscosity is moderate. So you can see after 1 minute it spread a little bit, but after 24 hours you can see the amount it spread, it's still in there, and after 96 hours you can see that it thinned down a little bit, but the spreading didn't spray much, because after a couple of as we can read, after a couple of minutes later, the area it spread with the gravity. After that it don't spread much. Okay, it's stayed kind of like, unless you have external factors, for instance wind or current. Okay, except for that it will be staying like that. In case of bunker fuel, it's didn't spread much at all, and it didn't actually uh, went out. Why is that? Because the viscosity is higher. Okay, so the volatility is low. Okay, so and that's why it didn't spread much. Okay, so this is a very important way, I mean to know, like, I mean the effect of the type of the oil, depending on the type of the oil, how it actually spread. Okay, now this is a illustration of like how Exxon Valdez, after a few hours, how the oil spill from Exxon Valdez work. Rate of spreading. Different types of hydrocarbon will spread over the water surface at different rate. Like for instance, it spreads quickly over the water immediately after the spill. Okay, the outer edge is always thinner than the inside. It's totally makes sense. Okay, imagine the frying an egg. This is a perfect example. Like egg is very viscous, right? So when you actually try to fry the egg, then you will find like that the middle, the most concentrated and more heavier, but the outer side is more thinner. Okay, because of the gravity, right? And also due to the surface tension. So this is another very important example, like the very similar to the frying to the egg. Okay, so after a day, the spreading effect diminish. We have seen that in here, right? After a day, so I mean, the 24 hours it spread this much, but after 96 hours, we have seen it's very similar, unless we have these effects. Okay, these we call weathering effects. Now, this is another very important curve, and it shows like the area it spread. So this is the time and the area oil can spread, and what's happened, like after these days, this is a log graph. Okay, so for instance, this is minute, so this is after 1 minute, after 5 minutes, after 10 minutes, after 50 minutes, after 100 minutes, and then after 1 day, after 7 days. So if a oil spill based on different types, how much area it would actually cover. Okay, so if it's a gasoline, then what's happened? It spread much for a couple of minutes. Okay, for instance, for an hour, nearly an hour, it spread the highest, and after that it started gone. Why? Because it evaporate. We have seen that at this picture, right? It starts evaporating because gasoline is lighter component. But for the crude oil, for instance, what's happened? It's spread. Okay, here for diesel, for the bunker. Okay, so after 1 day you'd find, like, I mean, it don't spread much. Like, I mean, the initial spreading is very high, but I mean, from 1 day to 7 day, the spreading rate of spreading is much lower. Okay, because of the surface tension and due to the gravity. Okay, so this is a very important graph, because in our project work we'll actually work with these different types of graphs. Okay, now debris can slow the wells leak. Yeah. um, Sinking and overwashing. So just imagine this is the spill source, and after 10 hours later, the Exxon Valdez. This is the graph of the Exxon Valdez. This is the area. It actually spread the crude oil. Okay. Now, rather than sinking to the seabed, the oil may sink at the lower and denser layer of the water column. Now, what's happened? Sometimes the heavier oil, okay, it can go under the water. As you know, like the why the oil actually float on the water, because the density of oil is lower. However, the density of heavy crude oil is like 1.02 gram per cc, but the seawater is 1.03. Okay, and the fresh water is 1. So what's happened, that the density difference between the heavy crude oil and the seawater is not much. So sometimes the oil can actually go in between the water. Like, I mean, like this is the water. Okay, now oil you can find in a layer inside the water column, and this is a kind of like a very dangerous, because from the top you cannot see the oil. Okay, but the oil layer is still in here. Okay, so we call this overwashing. That means this is the water, and water wash over the oil slick. Okay, so it occurs when the seas are not high and warmer, and fresh water from the land override to the densely seawater. Okay, so that means, like, this is the seawaters, for instance, 1.03 gram per cc. This is 1.02 gram per cc, but at the top you have the fresh water sometimes, okay, 1 gram per cc. It got less time to intermix, so the density of water is lower. So in that case, this overwashing can happen, okay, and it definitely complicate the cleanup. And it happen the heavy crude oil or bunker sea oil, this can work. Although this is rare occurrence, but this can happen for the heavy crude oil or bunker sea oil, okay. Now, overwashing frequently occurs and that hampers the cleanup. And the oil slick can disappear from the view, so it would be a big challenge uh, to, uh, to detect it, all right? Spill model. Spill modeling. Let's learn about the spill model. In order to protect the sensitive resources in the shoreline, the spill response team need to know the direction that the spill is moving. Okay. Now we use our advanced computer system to model or like to predict the spillage, the trajectory, pathway, the fate of the oil. Okay, so the typical output is shown in here. So we'll actually see that, but before that, let's see a video.
Hi, a quick update on our drifters for the Deepwater Horizon BP oil spill. This new trajectory they're forecasting at University of South Florida is extremely scary. I mean, boy, it's really changed a lot in the last couple of days since I last had time to update myself on this. As you can see here, here's Deepwater Horizon. Before it was like playing around up in here, but now it's like showing it just really getting caught up in a loop current, which you see here, going up like this and around and then going back this way, really going fast. I mean, here's Florida. Here's like, let's see, probably Naples, somewhere down in here. Tampa, I think somewhere right in here. So this is really starting to move south. So people need to really start paying attention and be sure that the Keys, Cuba, and then the East Coast are really prepared to deal with this going forward.
So what we have seen? We have seen how the oil trajectory actually works. Okay, so we have seen a good example of the BP horizon, Deepwater horizon, like how the oil trajectory actually works. So for instance, in here, as you can see, this is one of the output actually how the oil spill actually works. For instance, this is the occurrence area. Okay, from this point the spill actually happened, or like, I mean, for this source the spill actually happened, sorry. So this is the spillage source, and after a couple of hours later how the oil spill will be encompassed. Okay, so this is the after 3 days where it could go, and the effect of the winds and the channels and the shorelines. Okay, so we'll actually do these types of modeling in our project work, so you'll actually get more better understanding on that when we'll actually at the live session, when we'll actually see how this modeling can be done. Okay, now, the limitations of this model is definitely the lack of accurate estimation of water current and the wind speed. And also there is another limitation of the model is sometimes the physics, okay? Like there could be some other factors involving in here that we might overlook, okay? So that could actually limit our model, but it definitely can estimate the amount of evaporation, the possibility of emulsification, the amount of dissolution, the amount and trajectory of the dissolved component, the amount and trajectory of the portion that is naturally dispersed, and the amount of oil deposited and remain in the shoreline. So it can actually give a very good understanding on all of these components that we need. Okay, so we have seen the Deepwater Horizon spill. So this is the 3D model of that. Now, um, this is one of the example, like, I mean, how the models of the Deepwater Horizon models. So one of the model actually showed, like, this is the surface, water surface, okay, and this is the source at the ocean, bottom of the ocean, okay, the spillage happened. So for the lighter crude oil, it can go up, and after that you can see, but if the crude oil is heavier, then it can actually trap, like the overwashing the top, okay. So this is really scary. And I mean, because just imagine, like the sea, like the creatures, it can actually go to this trapped zone, and then it can die. I mean, those creatures can die due to the lack of the oxygen found in there, okay. Now, this is one of the example, like, I mean, how the bunker sea spilled in the St. Lawrence River, Canada. So when the oil spilled, or whether on water or land, a number of transformation process actually occurred. Okay, there are two major type of transformation, very important. Okay, number one is the weathering effect. Okay, and another is the process related with the oil movement. So the weathering effect means the series of process where the physical and chemical properties of the oil change after the spillage. For instance, volatility. Okay, so if the oil is volatile, then what's happened after a couple of hours, it start um, disappearing. Okay, and it will appear to the atmosphere, so which is also bad, but it will actually go out from the spillage source. Okay, now weathering and movement process, it can overlap, with weathering strongly influence how oil is moved in the environment. Now, this type of process very much depends on the type of oil spill and the weather condition during and after spill. Okay, the behavior process that occur after an oil spill determines how the oil should be cleaned up and its effect on the environment. If an oil evaporates rapidly, cleaner is less intense. For instance, gasoline. Why? Because the oil could evaporate. But the problem is the hydrocarbon will enter to the atmosphere, as I said, and it causes air pollution. Okay, an oil slick could be carried by a surface current or wind to a bird colony or to the shoreline. So that is another very severe consequence of the oil spill. Okay, and an oil slick could carry it out to the sea where it disappears naturally, and could have little direct effect to the environment, which is the best possible scenario. Okay, now the fate and the effects of a particular spill are determined by the behavior process, okay, which are in turns almost entirely dependent on the type of the oil and the environmental conditions, okay, at the time of the spill. For instance, if the oil spill in the Gulf of Persia, for instance, okay, or like Arabian Sea, the environmental condition in there is way different than the Atlantic Canada. Okay, in Atlantic Canada, it's cold water. So what's happened? The evaporation rate would be much lower. But in case of Middle East, the evaporation rate would be much higher. So environmental condition is very important. Another very important type is the type of oil, as we know. Like if it's a light crude oil, in that case, there is more chance that oil could actually evaporate. But if it's a heavy crude oil, then in that case, the probability of evaporating would be much lower. Okay, so this is how the type of oil and environmental conditions relates with the fate of the or the consequence of the oil spill. Okay, now the spill responders or the persons or like the company who actually are responsible to clean up the spillage, they need to know the ultimate fate of the oil. Okay, and that is exactly why we need to do the spill modeling. Okay, so for instance, this is the spilled source, and after 3 days later, the spillage will be in this area. Okay, now if the spill response take time, like 5 days to come in the spot and start cleaning up, at that time they need to know the exact location where they have to clean up the oil. Okay, so that is exactly why we need to do the spill modeling, so that we can accurately pinpoint the position of the oil spillage after that 5 days later. Okay, and that is exactly why we have to do the spill modeling. So the previous model, exactly like that. So now you understand why we do the oil spill trajectory model. Okay, to get the idea that the spill response teams, they will come and they will work on that. Now, how the weathering affect, or weathering, or like the environmental condition, as we said in here, how it actually affect, it change the physical and chemical properties occur at the different rates. The weathering rate is usually highest immediately after oil is spilled. It depends more on type of oil than condition, and it's temperature dependent, as I said, and it's slower at the temperature approach to zero. That makes sense. Sometimes you can see like after a year later, the oil spilled, it wash on the beach like that. Now, types of weathering depend on the importance, like the sorry, these would be the most important, and after that these are rare occurrence. Okay, the first important is the evaporation. Okay, and emulsification, natural dispersion, dissolution, photooxidation, sedimentation, adhesion, interaction with mineral fines, biodegradation, and the formation of tar balls. Let's see what are these weathering effects. Evaporation we know already. So evaporation, the rate of evaporation is very rapid immediately after a spill, and then it slows down considerably. Okay, why? Because, for instance, it's light crude oil. Okay, so the light crude oil got, for instance, a percentage of lighter component, B percentage of moderate component, and C percentage for heavy component. Okay, now in case of lighter crude oil, if it spills, so the A component will within like 24 hours it will evaporate immediately. So only B and C percentage would be in there. Okay, for instance, this is the A component is 50% in the light crude oil. But in case of heavy crude oil, the A percentage for the light crude oil is, for instance, only 20%. That means if it evaporates, still you will find this 80% of moderate and heavy portion of the oil would still remain. Okay, so that means the immediately after spill, then it slow down considerably. Okay, 80% of the evaporation occurs first 2 days of the spill. That means the higher, and some portion of the moderate actually evaporates, but the heavy crude oil, it don't evaporate at all, right? The evaporation of most oils follow the logarithmic curve over the time. Okay, that means the lighter components goes very quickly, and the heavier very slowly. Okay, some oil, including diesel fuel, evaporates as the square root of time, at least for the first few days. Okay, very alarming. Now the evaporation, let's see how the evaporation actually works for gasoline. So this is the time and this is the percentage of loss, that, or you can say like the rate of evaporation. So the gasoline, you can see a ramp, a very sharp ramp. That means it evaporates way faster than definitely the diesel. For the crude oil, like light crude oil, is more because it got more portion of the gasoline. Okay, but for heavy crude oil is slower. For bunker oil or IFO, which is heaviest of the component, even way smaller of the evaporation rate. Okay, so this is a very good a very important graph to show how evaporation actually works for different types of the crude oil. Okay, and evaporation is the most important weathering effect. Okay, now the properties of the oil, it changed significantly with the evaporation. So if about 40% of the oil evaporates, then what's happened? Then the viscosity could increase as much as 1000 times, which is very alarming. Okay, so the viscosity could increase. For instance, the light crude oil, it's as I showed before, uh, if the lighter portion actually goes by, so only the moderate and heavy portion will remain, and that's why the viscosity would actually increase. Okay, so the density would increase, the rise by 10%, and the flash point could rise by 400%. Why if the viscosity increased more than I said alarming? Because if the viscosity is higher, it is difficult to clean up. Okay, so that's exactly why. Emulsion, emulsification. Uh, Emulsification is very, I mean, it happens frequently and it's a very bad thing. Why it is bad? Because the liquid, when the liquid is dispersed to another liquid, it forms a small droplets. It don't actually mix. What's it happen? It actually creates something like mousse or like foamy type. Okay, foamy types of emulsions, just like the chocolate mousse in real life. Okay, so chocolate mousse is actually water and oil emulsion, like that. Okay, so the very same thing, like the whipped cream type. Okay, so this is actually looks like the emulsion. Now emulsion is very bad. Why it is bad? Because it's really difficult to clean up the emulsion. Why? Because the properties of emulsion. So see, energy forces the small water droplets. I mean, the once the oil and water droplets, okay, it slowly comes to the near, and then it actually collide with each other, and then the emulsions actually create. Okay, so water presents in four ways. Some oil contain 1% soluble water, or like the water entrainment, or like the semi or mesostable emulsion, or like stable emulsion. Stable emulsion is the like the largest challenge. Okay, it can stable for weeks or months. Semi emulsion or semi stable emulsion, its viscosity is higher. That's why it is a big problem to clean. Okay, so this is the emulsion actually looks like. Now emulsification, it increase the viscosity and it increase the volume also. Okay, and this makes the cleanup more difficult. Okay, because emulsion is a very I mean, the stable emulsification is impossible to disperse or recover with the skimmers or even to burn. Okay, so that's why this is big challenge. As you can see here, emulsion sometimes becomes stable for longer time. Okay, sometimes you can burn, but it's really difficult. Natural dispersion, it occurs when the droplets of oil are transferred into the water column, okay, by a wave of action or turbulence, okay. Depending on the wave energy or the sea energy available, natural dispersions can be insignificant or it can remove the bulk oil, okay. This is an example, the sea wave and the water. Dissolution. The process of dissolving occurs immediately after the spillage. A very small portion can actually dissolute, okay. So some most of the soluble component of oil are lost to the water under the oil slick, okay. Only a fraction of oil actually enters through the water column, and this does not measurably reduce the mass of oil. The significance of soluble aromatic is the toxicity to fish and aquatic life, and if spill with a higher percentage of aromatics occur in a shallow water, okay. Gasoline, diesel, and light crude oils are most likely to cause aquatic toxicity. Okay, a highly weathered oil is unlikely to dissolve in water. So, as you can see, the photo from Exxon Valdez village, okay, and it shows how slicks can often contain some emulsified oil. Okay, photooxidation, it occurs when the sun's action on an oil slick causes oxygen and carbons to combine to form the new products. Example of the new products, for instance, resins, and most soluble and dissolves, it can cause oil water emulsions. Okay. Um, Sedimentation, adhesion to the surface, and interaction to the minerals. Now, sometimes the spilled oil, it can actually interact with the sediments, okay, and the oil deposition can actually occur, okay. Um, Adhesion is same because oil is very adhesive with the rock or different types of it, so we have to be very careful on that, okay. So you can find all these in the slides. Biodegradation, sometimes the microbiological microbes, they can actually degrade the petroleum hydrocarbon, which is a favor they actually do for us. Okay, so the bacteria, fungus, it can metabolize the petroleum hydrocarbon as their food source, and it creates energy by eating up the hydrocarbons. Okay, so this is great. Now, the rate of biodegradation, it depends on the nature of the hydrocarbons, temperature, okay. As the temperature increase, the biodegradation rate will increase, okay, because the biodegradation work like a catalyst. However, some function is better at lower temperature. For instance, this cyclophilic type. So these are the cases of the biodegradation. Now, biodegradation, the highest rate is at the for the saturates. Okay, lowest rate it occurs for the aromatics because the chains are too stable to break it down. Okay, and kind of like bunker CO fuel oil also. The dissolved oxygen, that is a very important part of the biodegradation because the microbes also need oxygen to grow up. Okay, so that's why dissolved oxygen is very important. This is one of the example of the biodegradation. Okay, formation of tar balls. Sometimes the heavy crude oil can create a thick oil tar, okay. So this type of tar actually can occur. So the tar ball, it is remnant of the heavy crude oil or the bunker sea oil, just exactly look like that. So this would be all for this topic, but what is important now is you actually go. I already gave you at the resource section of the module this website. we would know, and this website also, okay, how to download this software, the GNOME software. Okay, so I would highly suggest you to, I mean, go to this site and then download the latest version of this software. Okay, and then we'll actually start working on the model. I will actually show you how to do the modeling part at our live session, so that you can be prepared for the project work. Okay, and I will actually give you the case file and cases, like, I mean, which area you have to do the modeling. All right, so take care and have a good day to you all. Bye.